Okay, it's time to start. So I guess if we just finished midterm, and I think finish midterm is almost graded, and we will return midterm sheet next Monday. Okay, and yeah, so we'll discuss midterm, and we'll also do a bit of midterm explanation on Monday. So today we will continue with our properties of Fourier transform. Okay, so it was our midterm. We talked about a lot of property, and we ended the property here. Okay, so this is a convolution property. Okay, and convolution property. Well, convolution property of Fourier transform is. It's not a particularly hard property, but it's a big topic today. Okay? The property itself is pretty obvious. It says that if you have a convolution of two signals, so if your y of t is a convolution of two signals h of t and x of t, then you do Fourier transform on y. The Fourier transform on y is big Y of j omega will be the multiplication of the Fourier transform of h and the Fourier transform of x. Okay? And yeah, so the property itself is just this. So you have a convolution on time domain, and you got multiplication on the frequency domain. And the derivation is also pretty straightforward. So is you write your y of t as a convolution of x of t and h of t, then you just Fourier transform to big Y with this Fourier transform equation, and you change the order of integration. This is something that you usually do when derive those properties. So you have an integration on tau and the integration on t, then you change the order of the integration. So you do integration on t first and then integration on tau, and you do some change of variable. You see that this integration on t with small h is become big H, and the remaining integration on x will be give you this big X. Okay. So the property itself is pretty straightforward. Oh, sorry. I think I should change this a little bit. Wrong. This one. Okay. Yeah. Okay. Yeah. The property itself is pretty straightforward. What's interesting is its interpretation on LTI system. So this is why we write small h and small x here. So this should remind you that this looks like this y equal to small h convoluted with small x looks like an equation for LTI system. And indeed, you can think of this as input-output relationship for an LTI system. So if you have x of t as input and you have an LTI system with small h of t as the impulse response, then you know the output is y of t. Then we know then this equation shows you, then this property shows that you can take a Fourier transform on your LTI system. So think about the Fourier transform of input of your LTI system and the Fourier transform on the output of your LTI system. Then they are related by this equation. So Fourier transform of input of your system and Fourier transform of the output of the system, they are related by output is input multiplied by this big H of j omega. And by the equation written here, this big H of j omega equal to the Fourier transform of small h of t. Okay, and but you might think that okay, so this is a conflict of notation because on chapter 3 we also talk about another big H of j omega. We say big H of j omega is the eigenvalue of your LTI system. Say big H of j omega is the eigenvalue of e to the j omega. Okay, but then you think more about this, then you see that the notation exactly fits. So this big H of j omega here, this is that was defined as Fourier transform of small h of t is the same as the big H of j omega that we defined on chapter 3. Okay, so here is a few reminder on chapter 3. Okay, so chapter 3 we says that we define this big H of s. When we were in chapter 3, we don't know anything about Fourier transform. We just try to derive the eigenvalue of e to j omega, and we see that we try to derive the eigenvalue of e to the st. So this s is j omega. Okay, so we derive the eigenvalue for e to the st. Then we see that big H of s equal to this integration small h of tau e to the minus s tau d tau. And then we change s to j omega, so we restrict to complex exponential e to j omega t. Then we see the big H of j omega equal to integration small h of t e to the minus j omega t dt. Okay, and we say this big H of j omega is eigenvalue of e to j omega t. Means you input into a j omega t into your system, and output is big H of j omega e to j omega t. Okay, and but you think a bit more about this. But you look at this equation and you realize that this is a Fourier transform equation of small h of t. Okay? Because we say Fourier transform is you take your function here and times e to the minus j omega t and the integration. Okay? So this is exactly the Fourier transform of small h of t. And that's a bit of the next slide, but let's finish this slide too. Okay, and also this interpretation. So this big H of j omega, excuse me. So this big Y equal to big H times big X. If you think a little more about its interpretation, you see that this is same as the eigenvalue, eigenfunction analysis we had. So you think about big X. If you think big X is the same as AK, and big Y is like BK, but now it's in continuous case. So big X is like the coefficient for e to the j omega t, and Y of j omega is the coefficient of e to the is the coefficient of the input signal e to the j omega t, and Y of j omega is the coefficient of the output signal on e to the j omega t. Then by the eigenvalue, by this equation, this eigenvalue equation, we know that the coefficient on output should be the coefficient on input times big H from here. Okay, and so this is similar to I guess this is analogous to what we had in chapter 3. We will say in chapter 3 we have BK equal to H times AK. Okay. So let me try to write one more equation. Oh, sorry. Let me do some routing here. Yeah. So this the routing. Yeah. Okay. Yeah. So this big Y equal to big H times big X is analogous to chapter 3. We have BK equal to big H of something and times AK. I think it should be JK omega naught here, if I recall correctly. Okay, so it was something like that. Yeah, K omega naught was omega. Okay, yeah, but it's really hard to read here, so maybe let's read this somewhere more. Okay, like here, BK equal to H over J omega naught, JK omega naught, and JK omega naught, and times AK. This is what we had in chapter 3, but now we are in chapter 4, and our spectrum is not discrete on just those discrete K omega naught. In chapter 3, because our signal is periodic with this fundamental frequency omega naught, so we only have frequency component on K omega naught. But in chapter 4, now our signal is aperiodic, and our Fourier spectrum is continuous on any omega. So we are not restricted. We are not restricted to this AK and BK, and we have this for big X and big Y, and they are still related by big Y equal to big H times big X. Okay. And yeah, so convolution property, we see that it has a very nice interpretation on this this different view on LTI system. And yeah, so this is the basis of a lot of our analysis in this course. That is, we see that LTI system, we will say this is viewing time domain and frequency domain. So in time domain, we see that we want to calculate the output. So the output as the signal of time, and related to the input as the signal of time is just output is a convolution of this impulse response with the input signal. And then we see that we can Fourier transform everything to the time domain. Then we get arguably even simpler equation. Then we see this frequency output in the frequency domain just equal to this system function in system function, which is the impulse response in the frequency domain times input in frequency domain. Okay, so big Y equal to big H times big X. Okay, and yeah, so this is some nice insight we learned from this convolution property on LTI system. And now we know that the Fourier transform of small h of t is big H of j omega. Then we know something nice because we know there exists an inverse Fourier transform. Okay, so in chapter 3 we only know how to calculate big H from small h, but now we know how to calculate small h from big H also. So we just apply the inverse Fourier transform. So then you can calculate small h from big H. So small h equal to 1 over 2 pi integration minus infinity plus infinity big H over j omega e to the plus j omega t d omega. Okay, yeah. So this is the extra thing we learned from this insight, that is how to calculate small h from big H. You imply the inverse Fourier transform. Okay, and there are more properties that you can derive from knowing this connection, knowing this transform to frequency domain. That is, so say there is a commutative property of LTI system. We were saying that you apply small h1, then apply small h2 is same as apply small h2 and small h1. And now you go to frequency domain, you easily see that the ordering of the applying two system is doesn't change the output, because you think about in frequency domain, you apply big H1 and big H2 is multiplying your big X with big H1 times big H2. And but now this is straightforward multiplication, then ordering doesn't matter. So this is applying big H2 and applying big H1. Okay. So I guess this is related to, you can think about there is a small h1 and a small h2, and there is a small h2, small h1. Okay, this is the ordering. And now back to, okay, so now we would like to see back and forth how the LTI system works in time domain and frequency domain, and we establish this Fourier transform pair between small h t and big H of j omega. But there is some caveat. So remember that Fourier transform don't always converge. Okay, so if you want, I guess I should write it here. Okay, so now we are considering this equation. So we have is Fourier transform pair h small h of t between and big H of j omega. Okay, and we want to use this to analyze our system. And we want to use this to analyze this system. Then we need to make sure that the Fourier transform actually converge. So in particular, we want the big H of j omega to actually exist. Okay. And they don't always exist, because as we know, for a lot of signal, okay, although this is a bit funny, so maybe I should say for a lot of function, it's a Fourier transform doesn't exist. Okay, it's a bit funny to call h of t as a signal, because it's impulse response, it corresponds to a system. Anyway, we want the big H of j omega to exist. And then we look into Dirichlet condition, and we see that, well, there are 3 Dirichlet conditions, but one of them is mostly violated. That is this absolutely integrable condition. Okay, and yeah, so you want usually, so yeah, so excuse me. So a big restriction is you want the h of t to be absolutely integrable. That's this integration minus infinity to plus infinity. Absolute value of h of t should be a finite value. Okay, and okay. So here the logic is kind of fuzzy, but we will sketch the the outline. So outline is if the system is stable. So if your system is stable, then from what we learned in chapter 2, we know that it's stable if only if small h of t is absolutely integrable, and then if it's absolutely integrable, then it satisfies the first Dirichlet condition. Okay, and then obviously there are two other Dirichlet conditions that you need to satisfy, but if you are satisfied, then we know your small h of t satisfy all three Dirichlet conditions, and big H of j omega exists. Okay, and so now we kind of pretend that the other two property doesn't exist. Okay, so we just say usually when your system is stable, then big H of j omega exists, and we can use this Fourier analysis to analyze your LTI system. Okay. And so mostly restrict ourselves to stable system when using the Fourier analysis. And but you might also what about unstable system? Then that's also covered in this course. That is when we introduce the Laplace transform in chapter 9. Okay, but for now we restrict to a stable system where we have Fourier transform of small h of t. Okay. That's about convergence. So this is just a note and something that we'll talk about later on chapter 9. Okay, and let's think look at some example of the small h of t and the big H of omega for different LTI system. And first we start with one of the simplest LTI system, that is this time delay system with h of t equal to delta t minus t0. Okay. And so you can do Fourier transform on this, and the integration is pretty easy. You will see big H of j omega because you are integrating on a delta function. You see big H of j omega equal to e to the minus omega t naught. Okay, and so you can write down this time domain. Frequency domain equation. So big Y equal to big H times big X, and then you write down this big H. So big H is e to the minus j omega t naught, big X of j omega. And now we go back to time domain. So we do this calculation on frequency domain, and then Fourier transform back to see what's Y of t. So Y of t is, and on this side you have this e to the minus j omega t naught, big X of j omega. And you see that this is the time shift property. You can use the time shift property to see its inverse Fourier transform, and it is x of t minus t naught. Okay, and so you see that is going to frequency domain, do calculation, and Fourier transform back, give you the correct answer that you expect. So because this is the time delay signal, and if you just do convolution with your input signal, you see is x of t minus t naught. Okay, so this is the first example. And the second example, and we are going to break something we said. So we say we want to study stable system, and then we give you a stable system, we have a differentiator y of t equal to dx dt. Okay, and now we go straight into the frequency domain, and now I guess we use the differentiation property, and we can go to the frequency domain, and we see that big Y equal to j omega big S of j omega, and then you compare this with our big Y equal to big H times big X, then you see that the big H for this differentiator is j omega. Okay, and so we find out the frequency response. So we find out the frequency response we using this big Y equal to big H times big X. Okay, and let's look a little bit more into this system, and now remember. So this is actually a really weird Fourier transform pair. Okay, so So if you calculate the small h of t, then remember this is the definition of our unit doublet signal. So h of t is the differentiation of delta function, is u1. And so here we got a very singular Fourier transform pair, u1 Fourier transform to j omega. And both sides of the integration is really not convergent, but you can somehow define these two as a Fourier transform pair. Okay. And anyway, let's look into another singular example that's still singular but a bit nicer. That's integrator. Okay, so while t equal to integration minus infinity to t x of tau d tau. And in this example, we go from time domain to frequency domain. So we start with impulse response, and we have seen the impulse response of integrator is this unit step function u of t. Look at this. And we will try to do Fourier transform of this thing. The integration is not very convergent, but in a previous example, we have calculated that it's a frequency response. Okay, so now we are doing a bit of circular logic. Okay, so in a previous example, we use the integration property, and to derive that the Fourier transform of u of t is this 1 over j omega plus pi delta of omega. It has this weird divergent pi delta of omega part. Okay, and now now we can check that this big H of j omega actually check out with this integrator. So we put everything into frequency domain. So big Y equal to big H times big X. Then big Y equal to big X divided by j omega times plus, and this part times big X. So pi big X of j omega delta omega. And because you have delta omega here, so you can put this big X just at the value of omega equals 0. Okay, and so you see 1 over j omega equal to big X of j omega over j omega plus pi x of 0 delta of omega. Okay, and this check out this check out with what we know because it's integration, and then we have the integration property that says if you do Fourier transform integration, then you got this thing. Okay? And but here we are really doing kind of a circular logic. So we use the integration property to derive the Fourier transform of unit step function, and then we use the Fourier transform unit step function. Fourier transform of unit step function to derive the integration property. So we are just saying that these two properties is consistent, and if you want the actual derivation, then I believe that you need to derive this Fourier transform of u of t from other properties, and actually do this, and then you can derive integration property. Okay, so so if you want the logically consistent derivation of those two properties, then you need to start somewhere. And if I recall correctly, usually people start from this derivation of u of t, Fourier transform of u of t. Okay, but I will not cover the derivation. You can look up some online source. Okay, and now let's go back to more example of LTI system and the impulse response. And now we go to less singular but more engineering example. That's filters. And here we don't do much of calculation. I just show you some idea. So remember, ideal Lopez filter. Look at this. You filter out everything that's not within this range. That's minus omega c to omega c. Okay, and well, the filter. Look at this. It's a block signal, and we have learned the Fourier transform of the block signal is the sinc function. Okay, so in a frequency domain, look at this. Then in a time domain, we'll look at the sinc function. It's this oscillating function. Okay, and now we think a bit engineering. Then we see that if we want to design a system that has this impulse response, then it's probably pretty problematic. So first, it's not coastal, because you have a signal that this h of t has a value when t is bigger than 0, and also it oscillates. Okay. Oscillates means that it doesn't converge very nicely, and kind of corresponds to that when you do Fourier transform on this thing. Fourier transform in finite region, then you always got Gibbs phenomena at the edge. Okay, so we want something that doesn't oscillate and it's causal, and so we can design. We can design our frequent LTI system with impulse response like this. So instead of this two-side decay and oscillation, we just have one-sided decay. Okay. So I said something wrong with the causal. So it's not causal because it has okay. It's not causal because it has value when t is less than 0, not bigger than 0. Okay. Impulse response should not have a value before t equals 0 for causal signal. Okay, and anyway, so now we have the causal signal. H of t is just exponential decay when t is bigger than 0, and then we can do Fourier transform of this signal, and then we see that the frequency response is this thing. Okay, we have done this integration before. This is 1 over j omega plus 1, and the absolute value of frequency response look like this. Okay. And I think we will actually construct this in chapter 3 already. This is what you can construct from the RLC circuit. And so you see that it's not an ideal filter anymore, but it kind of looks like filter. It's a bit higher in the middle and going lower and lower when absolute value of omega gets bigger. Okay, that's a bit of more example on small time domain and the frequency domain of the system. Okay, and the next example is an example that teach we a bit more math. Okay, this is a bit of a funny example, but the idea is very easy. Is once again we have a system and the impulse response, and we ask you to calculate the output of the system. Okay, and the two functions here are easy. It's two exponential decay with coefficient minus b, and then exponential decay with coefficient minus a, and all cut off at u t equals 0. And the ideal calculation is easy. You go to frequency domain and you multiply together and you try to do inverse Fourier transform to get the time domain. Okay, but here this example is an example where we introduce a pretty important mathematical tool. Okay, this tool we'll use a lot when solving differential equation. Okay, so this tool is for us to solve the inverse Fourier transform. Be nice, easily. Okay. I guess let's start with all the previous parts. So the easier part. So we have this e to the minus btu of t, e to the minus atu of t, and you do Fourier transform. We have done this before. So we look at our previous result. This is 1 over b plus j omega and 1 over a plus j omega. And then big Y is just big X times big H, and so it's this thing. Okay, and now we want to do inverse Fourier transform on this thing, and obviously you can just do the integration, but the integration will be pretty hard. Okay, so we use a bit of property to do this. So we try to break this Y as two fractions. Okay, so so if you look at it hard enough, you see it's 1 over a polynomial on omega. It's 1 over something plus omega and times something plus omega. And then we already know the Fourier transform of 1 over something plus omega. So we say, how about we break a big Y equal to into this some coefficient big A to be calculated over a plus j omega plus some coefficient b over some coefficient big B over b plus j omega. Okay, and if we can solve for this, and indeed we can. So if you solve this, you see big A equal to 1 over b minus a, and big B equal to minus 1 over b minus a, and big Y equal to those two terms, and then by linearity of Fourier transform, you see that the Fourier transform of big Y is the inverse Fourier transform of big Y is the inverse Fourier transform of this first term with big A and the second term with big B. And the Fourier transform of those two terms we already see is like a Fourier transform of those things. Okay, so inverse Fourier transform is 1 over a plus j omega is e to the minus at u of t, and the inverse Fourier transform of b plus j omega is e to the minus bt u of t. And yeah, so without doing any integration, you see y of t equal to this thing. Okay, you only need to do this is splitting of 1 over a plus j omega plus times b plus j omega to this something over a plus j omega plus something over b plus j omega. And I guess here we have an assumption here. So this is assuming b not equal to a. We can have this thing. Okay. And yeah. And so this trick here to break this 1 over polynomial into the linear combination of a 1 over monomial is called partial fraction expansion. Okay, so basically you want to solve for y, so big Y equal to, so yeah, so we want to solve for big Y equal to this big A over a plus j omega plus big B over b plus j omega. Okay, and so this is actually something you can do in general. So you have any rational function f of x equal to g of x over h over x, and g of x and h of x are polynomial. And now assuming that, okay, so we start with the easier case. Assuming so we care about the lower polynomial mode. Okay, so if the lowercase polynomial, we write it in this factorization, so it has the roots minus a, minus b, minus c, and if all its roots are different, then we are in a very easy case. And you can easily derive a theorem says that you can always write your f of x equal to this a over big A over x plus a, big B over x plus b, plus big C over x plus c, etc. Okay, where a, b, c are some constants that can calculate it from your small a, small b, small c, etc. Okay, and you need to solve this thing. Okay, and well, there are different ways to solve for a, b, c, and I guess easiest way is you just write the equation saying that this thing equal to this thing, and try to multiply all the denominators. And yeah, you just multiply about everything, and then you equate each side. You get some equation on A, equation on B, equation on C, and then you can solve for A, B, C. Okay, and yeah, and here we also have another disclaimer. So we say for any rational function g of x over h of x, we can always do this, and it's not quite true. We also need the degree of g less than degree of h for this to be true. Okay, and yeah, and but you can also deal with a case where degree of g is greater than degree of h. You just do kind of a long division on your polynomials. So you write your f of x equal to some quotient, some polynomial is as a quotient of g and h. So this is q of x, and then the remaining part you can do is a partial fraction expansion, and then yeah, you will think about the Fourier transform of q of x later. Okay, and anyway, so this is a small slide on partial fraction expansion. But let's go back to this case. And in this case, you multiply everything, and then you solve for a and b. You get this a equal to 1 over b minus a, and b equal to minus b minus 1 over b minus a. Okay, and but this only works for b not equal to a. And when b equal to a, you actually cannot do this because, well, you got 1 over 0 here, okay? And yeah, when b equal to a, then you just have 1 over a plus, x plus a squared, okay? And it cannot be breaking into partial fractions, and you just need to find the Fourier transform that is indirectly. And but once again, we have this idea of we don't want to do integration, so we use another property to find this inverse Fourier transform. Okay, so your big Y equal to 1 over a plus j omega squared, and here we use the differential property. Okay, so we still want to build on this Fourier transform of 1 over a plus j omega. Okay, and then we see that well. 1 over a plus j omega squared is you take a differentiation. Is a differentiation on omega of 1 over a plus j omega. So if you do the differentiation on this thing, you will get extra 1 over a plus j omega factor, and also you get then you also get a minus sign, and you get a j, and in the end you get extra j here. Let's see. Should be correct. Minus sign and yeah. So anyway, it should be correct here. Okay, and yeah, so big Y is j times the dd omega of 1 over a plus j omega. Okay, and now we can use the dual of differentiation. Okay, so on frequency domain you do differentiation, then on time domain you get h1 minus jt. Okay, so you see that the 1 over a plus j omega has a Fourier transform paired to e to the minus at u of t, and then you get h1 dd omega, then you get h1 minus jt here, and but you also get h1 j here, then you just get t here. Okay, and yeah, so this is yeah, and yeah, so this is the Fourier transform of sorry, not the Fourier transform. This is the output of the system where a equal to b. Okay, so when you have e to the minus at u of t and e to the minus at u of t, two of them as input, then the output is t to the minus at u of t. Okay. And then yeah, obviously you can also do just the convolution integration to check out the answer is actually correct. Okay, yeah, that's the partial fraction expansion, and I guess here we can, I guess any question now? Yeah. And but as we said, this is something actually very general. Maybe go back here. So really, this tells us how to do Fourier transform on any rational function. Okay, so you get any rational function is g of x over h of x, and usually want this to be stable. So let's say g of x has the degree less than h of x, and and then you can also always do partial fraction expansion into those monomials, and sometimes okay, and if you are lucky, then you always have just order 1 monomial on the down here, then you can just use this Fourier transform pair to get everything, and then if you have a higher order monomial higher order monomial here, then you need to use the then you need to use the differential property a few times, and to see that, say you have a 1 over a plus j omega, so you have a second order term here, then you get extra t here, and then you have like a third order term, then you will get even more order of t here, etc. Okay, so yeah, so this is a general strategy to get the Fourier transform of any polynomial, sorry, any rational function. Okay. So it's right here, and yeah, and here we have the writing of some other strategy to do partial fraction expansion, but I think it's okay. You can try to read it yourself. Okay, but anyway, so should say this is relativity of any rational function. Okay, yeah. So this is yeah, and this is really partial frequency expansion is very nice, and this is something we'll even use when we do Laplace transform, as you will see in the later part of the course. It's a nice mathematical technique. Okay, and 10 minutes. Let's look at more example of this convolution property, and here we have so now is an example that the convolution property really save our calculation. So we have x of t is a sinc function, and h of t is another sinc function, and they have a different frequency. We have omega I here and omega c here. And then we go to frequency domain, we see this is a block signal, and this is another block signal. Okay, with the first block is inside omega I, and the second block is inside omega c. And now we want to see the output while t equals to h of t convoluted with x of t. Then we first calculate the big Y, and we see that big Y is an interesting function. Is you have the multiplication of this signal and this signal, and you see they are trying to filtering out each other, and in the end you got another back wave, but the width here is the smaller of omega c or omega I, because whichever bigger one, then this one portion is going to multiply by 0, and 1 multiplied by 0 is going to be 0. Okay, and yeah, and you can Fourier transform back, and because it is a black wave, then you go back to sinc function. But you have two different cases for your sinc function. You see that if omega c is smaller, then your sinc function has omega c, and if omega I is smaller, then your sinc function has omega I. Okay, so this is an interesting example of our convolution property. Okay, and I guess we can talk a little more. So we have the convolution property, and we have about 10 minutes, and we can talk a little bit about the multiplication property, because we can restart here today, but restart here on Thursday. But let's try to talk a little bit about this. Okay, so multiplication property, and it's really a dual of convolution property, and so it looks very similar. So it says that you have multiplication on time domain, and you get this convolution on frequency domain. But you just get this h1 over 2 pi because of our syntax. Okay, and also the notation here is a bit funny. So your convolution on some big S of j omega and big P of j omega, and then you change the dummy variable to theta, so you have big S of j theta times the big P of j omega minus theta. Sure. And yeah, it's just some funny notation here, because remember our independent variable here is omega. We have like a big S of j omega here, and then you get hrj here, so you get hrj here and hrj here. Okay, and yeah, so this is really looks like the convolution property. Just have the hr2 pi here. Okay, and we can have just like the convolution property has the interpretation of the Cson equation for have the interpretation of the eigenvalue equation for LTI Cson. The multiplication property can also be viewed as you use one signal to modulate the amplitude of another. Okay, yeah. And this is called amplitude modulation. And so what do you mean by? I guess we will see example pretty soon. But anyway, you think about your multiplying two signal, then you can think about your I guess it is called modulation. So you multiply a signal with another time domain signal is called modulation, and this is called amplitude modulation. Okay, and yeah, so this is called modulation property. For now, this is notation here. And but anyway, let's see example of how modulation work out. Okay, and so we are modulating a signal with cosine signal. Okay, so we have some input signal S over T, and we try to do amplitude modulation of this cosine signal, cosine of omega naught T. And we already see something happen. This happening. This was I guess in midterm. So this is cosine modulation, but now we see this in this multiplication property. And anyway, cosine omega t equal to 1 over 2 e to the j omega t plus e to the minus j omega t. Okay. And then we go to the frequency domain. Okay. So the time domain signal is just you multiply this with the cosine, so it's pretty easy to see what's the output of a time domain. But now we want to see how this modulation affects the spectrum. So in the spectrum, the output signal will be, the frequency domain of the output signal will be affected by this convolution of your frequency domain signal with this frequency domain of the modulation signal. Okay, and so let's first calculate this big P of j omega. So big P of j omega is the Fourier transform of cosine omega t, and it is pi is 2 delta function. Is pi delta of omega minus omega naught plus pi delta omega plus omega naught. Okay, so it's this back here plus this back here. Okay, and now we see what happens when you have the convolution of your big S with this signal. Okay, and so you convolute big S with 2 delta function. Then you see that, but we already know the convolution with delta function is you just apply a time shift. Okay, so then you see that convolution with this delta omega minus omega naught give you S over j omega minus omega naught, and then you have this omega plus omega naught, you get omega plus omega naught. So you have a time advance and a time delay. Okay, and you work out the constants. Then this pi cancel with this 1 over 2 pi. Become 1 over 2, and similarly you have 1 over 2 here. Okay, and it's easier to see the effect we look at the picture here. So you have a quite arbitrary big S of j omega here. This is on frequency domain. This is on frequency domain representation of your input signal, and you convolute it with this 2 delta spike and minus omega naught and plus omega naught. Then you see that something very interesting happen. You see your signal in the frequency domain got split into 2 copies. Let's assume this omega naught is pretty big. So you are modulating with a slower signal. Okay, if this omega naught is pretty big, bigger than what your S look like, the frequency spread of your S, then you see that your spectrum got split into this part and this part. So both of them center around omega. So they are centered around minus omega naught and plus omega naught. Okay, and the height is 1 over 2 of the original signal. Okay, so so you see the frequency modulation can split the input into this input on 2 different frequencies. Okay, and we also think about how you turn this back. Okay, so you can modulate your signal into those 2 signals that center around much lower frequency and a much higher frequency. I guess both much higher frequency, but higher frequency a negative value and a positive value. Okay, and a way to do demodulation is so I guess we are short in time, so let's talk about how to do modulation first. And something interesting is you can modulate by just doing the same calculation. So once again, so you have this output, and they just modulate with the same cosine omega t. Okay, you just in a time domain, just multiply the signal with cosine omega naught t once again. Okay, and so you see do the same calculation. You are convoluting this signal with the same big P, and you know that those two delta will give you one half time shift, one half time advance, and one half time delay with omega naught. And so then this signal was split into two, so there was height 1 over 2, and it was split 1 over 4 at minus 2 omega naught, and 1 over 4 at 0, and this one was split into 1 over 4 at 0, and 1 over 4 at 2 omega naught, and then you see that if you you see that in the middle part around frequency omega. Around frequency 0, this looks like the input signal, and there are half of the signal at this minus 2 omega naught and plus 2 omega naught, and those are high frequency component, and what you do is you apply some filter, try to filter them out, and you can get, you can almost get your signal back, but it's lower, you get a lower amplitude, so if you won't get the full signal back, you need to do some amplitude amplification. Okay, and anyway, that's some idea about modulation and how you look at the length through this multiplication property. And we'll talk more about multiplication property on Monday, and also discuss midterm. Okay, so see you on Monday. Okay.